Numerical Computation, Chapter 2, Video number 3. The topic of this video is Newton's divided difference. As we discussed at the end of the previous video, we wish to have an algorithm in a recursive form that will generate the interpolation polynomial for a data set. So the main idea is the following. So given a polynomial pk, a polynomial of degree k that interpolates k plus 1 data points, let's say an xij, where I goes from 0, 1, 2, all the way to k. And we wish to find the polynomial pk plus 1, that is a polynomial of degree k plus 1, which would interpolate all the data points that pk does, plus one extra point, let's call it xk plus 1, yk plus 1. By using the polynomial pk we had earlier and adding an extra additional term in a particular way. Now let's go through some derivation for this construction, starting from the simplest case where n equals to 0 and we have just one data point x0, y0. And we will fit in a polynomial of degree 0, which is a constant, which shall equal to exactly the y0 value. So for any x, the polynomial p0 returns the y0 as its value. So clearly this polynomial will interpolate the first data point x0, y0. Now we add one data point x1, y1. So two data points and n equals to 1, and wish to find a polynomial p1 which interpolates those 2 points. And we want to write p1 in the following way, the particular way. That is, it equals to p0, the p we got at the previous step, plus an additional term in this particular form. It is an a1, which is a parameter to be determined, times x minus x0. Why did we choose this special form? The reason will become clear now. We want the polynomial p1 to interpolate all the points that p0 interpolates. So by using this special form, then we see that p1 evaluated at x0 will simply equal to p0 evaluated at x0 plus a1, and putting x equals to x0 and the additional term gives a contribution of 0, so it doesn't change the data. So this will equal to y0, which means p1 interpolates the data x0 and y0 for any a1 coefficient. The coefficient a1 can be determined by using the interpolation property of the additional point we add. So p1 at x1 must equal to y1. So plug it in, x equals to x1 in the polynomial, we get p0 at x1 plus a1 at x1 minus x0. So p0 is a constant function, so this simply equals to y0. So we basically have this expression shall equal to y1. And we see that a1 here is the only unknown, and we can solve for a1. So some algebraic manipulation, moving y0 to the other side, you get y1 minus y0, and moving this factor to the other side, and it comes down to the denominator. So this is the expression for a1. So one could probably plug a1 back into the original equation number 1 here. If you put in a1 with the expression we obtained below, then we can write out the polynomial p1. Now let's take one more point and we want to find a polynomial that interpolates 3 data points, and x0, x1, plus an additional one, x2 and y2. So this is a polynomial of degree 2, and we want to write it, construct it, such that p2 equals to p1, that's the one we get when n equals to 1, plus an additional term which takes this form, a2 times x minus x0 times x minus x1. So the reason why we choose the additional term in this particular form now is quite clear, because at the previous interpolating point x0 and x1, this additional term exactly equals to 0. So the interpolating property of p1 will be preserved in p2, which we check now. p2 at x0 will be p1 at x0 plus 0, so it's y0. And p2 at x1 will be p1 at x1 plus 0, which is y1. Therefore, p2 interpolates at the point x0 and x1. And now, in a similar way, the coefficient a2 can be determined by using the last interpolating point, which is x2, y2. So p2 evaluated x2 must equal to y2. Plug that in, we get this expression. So this is p2, where we put x into x2. So that equals to y2, and in here a2 is the only unknown, and we can solve for it by moving all the terms to the other side of the equation. So after some manipulation, we see that after moving p1 to the other side of the equation, we get y2 minus p1 at x2 in the numerator, and the denominator is exactly this factor moving over to the other side of the equation. So it's x2 minus x0 times x2 minus x1. Plugging in the expression for a2 back into this polynomial p2, and now we can write out the polynomial p2. Now, this expression of a2, comparing to the expression of a1, and it doesn't really show us some iterative or recursive relation between them. So what we will do now will be, we will manipulate this expression of a2, and we write it in a specific way so that we see some connections. So in particular here, you will have to evaluate p1 at x2. So we'll first have to write out what exactly is p1. Okay, recall the expression for p1. p1 of x equals to y0 plus, and this is your a1, times x minus x0. So we need to evaluate p1 at x2 for the computation of a2. So let's first figure out what does that equal to. So plug it in, x, change x into x2, and then we have this expression, where it's the same as the previous one, by substituting x into x2. We now do some manipulation. So it's a standard manipulation. So this term here, I'm going to write it into another way. So that equals to x2. So what I do is I subtract an x1 from it, and then I add the x1 back. So I did nothing, right? So I added 0. Okay? And I group the first two terms and the last two terms into two groups. So the advantages of doing this would be, now after the distribution of multiplication, this term here will cancel that term. So let's see what happens after we distribute this factor into this term and into that term. Now we see this one times that is left here, and then this one times this, and we see that they are the same x1 minus x0, x1 minus x0, so they can actually cancel each other. And after the cancellation, now we see we have y1 minus y0 here, and I have some more cancellation, so negative y0 would cancel y0. So this term cancels that term, so all that remains out of it is just a y1. So which is exactly this expression we have now. Now we can plug this into the expression of a2 and rewrite it. So this is the expression for a2 we got, and where p1 at x2, we just worked out a new expression for it, and let's plug it in. And then after plug it in, we see this part is just p1 at x2, and then what will I do at this step will be I would divide both numerator and denominator by the factor x2 minus x1. So you see I will divide this by x2 minus x1 and divide the denominator by the same factor. So what does that do to me will be, okay, this will be cancelled and this will be cancelled, but this one here, the first term, will be divided by x2 minus x1. So clean it up, we can write it in a shorter form. Okay, so now this is what we get. Okay, take a look at this expression. So what do we have here? Let's look at this term, the first term, y2 minus y1 over x2 minus x1. So this term represents actually the slope of the secant line connecting the data point x1, y1 and x2, y2. So if the data point shall be points of some actual function, let's say a function is f of x, then this will be the approximation to the derivative of f, probably at the point x2. One can think like that. In this expression, you can think in a similar way. That is, it's the slope of a secant line between the data point x0, y0 and x1, y1, and that's some kind of a derivative of the function at the point x0, some approximation. So what we have here would be, let's write it, some kind of a derivative, approximately f prime at x2 minus, and then this one would be some kind of a f prime at x0. Okay, so what do we have? Well, we have thinking f prime as a function here, so it's f prime at x2 minus f prime at x1 over x2 minus x1. So that again is some kind of a secant line. So you can think that this is actually again an approximation of some second derivative of f at some point near x0 and x2. Also pay attention that this guy here actually is a1. So a1 is some kind of a approximation to the first derivative of your function. And now a2 is some kind of a second derivative of your function. So hopefully through this observation, I might have convinced you that these coefficients a here are actually related to the derivatives of the function f. So maybe a k with index k will be some kind of a f to the kth derivative at some point. Now let's look at the general case for an. So assuming that Pn minus 1 interpolates n points for I from 0, 1 to n minus 1, and we want to construct the polynomial Pn using Pn minus 1 and add on top an additional term that takes this special form. And now we shall be quite comfortable with this particular form. And that particular form exactly allows the polynomial Pn to preserve the interpolation property of Pn minus 1 at all the data points I from 0, 1 to n minus 1. And in a similar way, the coefficient an could be determined by using the additional point that you add on, that is, the point xn, yn. And put that in and write out, I have yn equals to this expression here, where you put x to be xn. Okay? If you compare this expression with that one, it's just setting all the x, change them into xn, and that's what you get. And you see everything here is given except an, which is my unknown. I can solve for it. A simple manipulation would give me an an of this form. So it's just Pn minus 1 moved to the other side, so I get y minus that, and this product goes to the denominator when I move it to the other side of the equation. So that is an. Now, after you have obtained all the coefficients a0, a1, a2, and all the way to an, one can write out Newton's form of these interpolation polynomials. So you can write it out as the way you compute. So you can first write a0, that's your p0, that's y0, and then you add the additional term you add on to get p1, so that's a1 times x minus x0. So up to here, this would be p1. And then you add on the additional piece to make p2, which is a2 times x minus x1 times x minus x0 and x times x1. And so on and so forth until you reach the last term, that is an times the product of all these terms. And this is called Newton's form for the interpolation polynomial. So as we see that, in this computation we went through, the key step would be to compute these coefficients, a0, a1, a2, all the way to an. If one can find an efficient way of computing them, possibly in a kind of an iterative way, and then the Newton's interpolating polynomial can be written out. So in the next video, we'll take a look at a specific way of computing these AIs, and they are called Newton's divided difference.